Hello everyone, my name is Reidy, and I'm going to be presenting our demo, HiRISE, or High Resolution Image Scaling for EdgeML via in-sensor compression and selective ROI. In computer vision, many applications involve multiple models with multiple stages. For example, in facial recognition, the initial model detects the faces and then the subsequent model identifies them. In these systems, only a small portion of the image is requiring a high-resolution image. For example, the faces are what's requiring a high-resolution image because in order to detect faces from far away, you need a high-resolution image so that you still have rich features in the faces once you've extracted them from the original image. This results in inefficiency because we must load the entire image in high resolution even though only a small portion of the image is requiring high resolution. This is because in a traditional approach, high-resolution images are transmitted from the camera or the sensor to the processor. Upon arrival at the processor, the images undergo compression. That way they match the resolution of the object detection model. Then a two-stage model is employed. The first stage identifies the regions of interest within the compressed images, and the second stage processes these ROIs to perform a specific task and generate the final output. In the case of facial recognition, the first model finds the faces, and the second model identifies them. This has some drawbacks though, because if we have a high-resolution image, we need a lot of analog to digital converters. This leads to energy-hungry signal conversion, high bandwidth requirement, and large memory capacity. In contrast, our approach compresses the image in the sensor and then transmits them to the processor. Then, same as before, a two-stage model is employed. The first stage identifies the regions of interest within the compressed images. Then, the region of interest coordinates are sent to the sensor, and only the portions of the image that need to be high resolution are sent back in high resolution. The second stage then processes these ROIs to perform specific tasks and generate the final output. This is a way more efficient approach because we reduce the overall number of analog to digital converters required, we reduce the overall data transfer, and we also reduce the memory capacity requirement. So in order to demonstrate this, we're going to compare various aspects of our HiRISE enabled face detection system with a traditional system. We're going to show you the difference in image quality, memory requirement, bandwidth requirement, and energy usage with a HiRISE enabled versus disabled system. In order to show our demo in real time, we're going to use a Raspberry Pi 5 with a Coral USB TPU. This Coral USB TPU can accelerate the face detection model in order to allow it to run in real time. We're also going to use a high-resolution webcam and a face detection model. The face detection model was trained on the crowd human dataset using the Yellow V8 Nano architecture and byte track object tracking. We then quantized the model to have 8-bit weights and activations. That way it can be compiled to run on the Coral USB TPU. In the demo, you see on the left a very low resolution image. This is the output of the in-sensor compression circuit. Even though it's grayscale and low resolution, the object detection model has no problem finding where the face is in this image. Next, on the right, you can see the output of a HiRISE enabled ROI extracted from the high resolution pixel array versus a traditional system without HiRISE. You can see that the HiRISE enabled system has better image quality than the HiRISE disabled system. Not only is the image quality better by 8 times, but we also reduce the peak SRAM required for the whole system. There's also 37% less energy and bandwidth requirement using HiRISE. In conclusion, using in-sensor compression along with selective ROI mechanism, we ensure only necessary information leaves the sensor. This enables the deployment of two-stage models in low memory environments. This also reduces the bandwidth requirement between the sensor and the processor. And finally, it reduces the energy consumption of the sensor because it reduces the number of analog to digital converters required. Thank you for attending this demo. If you have any questions, feel free to reach out. Thank you so much for watching.